it is not, it seems like 15, 17, okay. Yeah, 239. That's a drop. 235. The air? Yeah, 4.0.
Okay, so let's
yeah.
compare all six.
Yeah, so that's exactly.
Oh, 2 out of 2. 3 out of 3. 4 out of 4. Got 2 to go. Come on, guys.
Ladies and kiddies.
Turn this on camera so Eva Cooney can enjoy. Oh, we got 2 more. I'm gonna have to push this a little bit for focus, so I should do it. Okay. So for the people that have this one already and you're ready to advance a slightly harder problem. Well, I guess I have to do proportions before we go to that one. So we'll go back to Rutkowski. Who's second? First. So let's do 15A in lane. 15A, you can do this at your seats. We'll just check our answers. 15A. Okay, who's done? You should be right there.
I got
15A, you haven't answered.
uh,
It's wasted on me, I didn't do it. We'll wait till some other people do it.
Oh, I believe it's right. I just
Okay, how'd you do in 11 though? Did you get 11?
lady. Yeah, I got 11.
Does it agree with what's on the board?
Yes.
Okay, did you put it on the board?
This is
Yeah, we were waiting for you. That's what we were waiting for. Okay.
in lane. Oh,
This was
Yeah, it was in lane.
lane 15A.
Yeah, well, no, this is Nux. Nux didn't do 11 on the board yet, did you?
11 in Lane?
Yeah, did you do it?
Oh, I thought it was
That's
different.
Number 4.
That's number 4 we're doing.
Oh, I'm done, I'm bad, excuse me. Wait, oh, this is 4 Nalowski. So did you put that one up next?
No, I haven't.
Yeah, because we were waiting for you to do that, that's why we had dead time. Okay, so everybody now go to lane 15A. 15A. And we'll just compare answers orally. Lane 15A. Karen, you got your answer?
Yes,
What you have, please?
the interval is 54.508 and 65.492.
Okay. Now, I'll buy that, but, some might criticize it as being false precision because the data is not to that many, you only have the sample mean to sit to no decimal places. So you really should just have one decimal place in your conclusions. So your calculations should exhibit one more decimal place than your data for correct precision. But we're not going to be fussy in here, just let you know that will happen. See if we get any support for these.
It actually makes it easier not having all the extras.
Yeah, we can't round off to the last step, if that's what you're referring to. Oh, you mean all the other stuff on the board?
No, I mean, I was never clear on when I could just round up and have, you know, less places, but now that you said that, just go one beyond what those are, that makes sense.
That's standard, but not until the last step. You keep all that
Right.
intermediate accuracy. Lynn, same?
Yes.
Okay. So in a moment, I'm going to talk about, no longer talk about the mean, but start to talk about the other parameter that we take intervals on called the proportion. Okay. So I'll get a couple more verifications on this. Nux, was that your answer too?
Yes, sir.
Okay, Tayo? Okay, and Sean working?
Yeah, I started it.
Okay, good. Okay, now I'd like to expand our items. First, let's go to lane number 1. Lane number 1. When would the mean grade in a class on a final exam be considered a statistic, and when would it be considered a parameter? So Karen, could you tell us when it's going to be considered a statistic, and when's it going to be considered a parameter? First, a statistic is an aspect of A, a sample, or B, the population.
The population,
That's right, a sample.
right.
Statistics are aspects of a sample. Now, we learned this in week 1, 100 years ago. So it's just notation, nomenclature, it's not terribly important. but every once in a while it comes up. So a parameter is an aspect of the population,
Okay,
and a
because-
statistic is an aspect of the sample. So
Okay,
it's
well, the reason
PP.
is because whenever they talk about it, they, like you're saying, is 95% with an error will be potent, so to me, that's a statistic
I
of
know,
the
but,
population.
right, in the
Yeah.
general vernacular it is, but
Okay.
we're not permitted the general vernacular once we step into a technical class. We have to go with the exact definitions, and this is what they are, okay? So now, we know that if we're, so up until now, what we have done is take the interval for data that was described by a mean value, such as people's weights or people's IQs, people's heights, weights of elephants. They have a certain mean, agreed? In other words, they have units. But when you take the presidential approval rating, what you get is a percentage or a proportion, agreed? 47% of the population. The proportion of the population is 47%. This is a dimensionless number. It's a percentage or a proportion. And they also have a presence in the population, and they also have a presence in the sample, or they have a presence in the sample. And we're going to learn how to take a sample, evaluate the proportion in the sample, and reflect it back on the population with an error, the same way that we did with the mean. So the proportion handles almost exactly like the mean handles. And proportion comes from the binomial distribution. So suppose this is the binomial distribution. Suppose in the general population, 2 out of 5 voted yes on a certain referendum, agreed? Then in our notation of P and Q, we say that the numbers of P was 0.4 and Q was 0.6, because those are the probabilities of percentages of the population. 2 out of 5 is 0.4, 3 out of 5 is 0.6, agreed? And then we had a formula for the binomial distribution. If you take n members of the population, and you want to know how many x's in n, how many successes. X is a success. X is yes, success. You want to know how many x's. So you want to know, let's say, the probability of 3 x's and a sample of 10. So the general formula is C n to the x times P to the x times Q to the 1 minus x. Okay? So in this case, it would be C 10, 3, and it would be 0.4 to the 3 power and 0.6 to the 7 power. And this would give you the probability of taking a sample of 10 and finding 3 yeses in that sample of 10. This is the binomial distribution. We covered it 2 weeks ago, not in great depth, because this class, following Yudkowsky and Lane, some things they didn't emphasize, and this is one they didn't emphasize. However, what happens to the binomial distribution as you let n get taller, larger, and larger, is that these slices get narrower and narrower. And as you let n get even larger, then the slices even get narrower. So it starts to approach a continuous curve. So for a very large n, then it's no longer a discrete set of bars, but it becomes one continuous curve. So when the binomial distribution for large sample size n goes into a small curve, large curve, then it has a mean and it has a standard distribution. And the mean that it has is the size of the sample times P. And remember, P was the original probability of a yes vote, agreed? P is the original probability of a yes vote, N times P. In other words, it's the proportion of the population that actually voted yes. And the standard deviation of this curve is the square root of NPQ, where it's known. So this is the, this becomes the distribution of sample proportions. This becomes the distribution of sample proportions. So it assumes a normal shape, it's N. Now, it's the mean and the standard deviation. What is the mean? NP. And what is the standard deviation? Square root of NPQ. And this is describing this normal curve by these two parameters, the mean and the standard distribution, as any normal curve is defined by those two parameters. Now, if you scale up a normal curve, that is, you multiply everything by 3, do you still have a normal curve? It's just scaled up. If you take everything to 1/2, you still have a normal curve. It's just scaled down or up. So we can scale this curve by dividing both of these by n. And when you divide both of them by n, then what is the new mean? P. And what is the new standard deviation? PQ over the square root of n. Because here you have a square root of n in the top and a whole n in the bottom. So let's do that slow motion. If I have the square root of n, p, q, and I divide that by n, that's the square root of n, the square root of p, the square root of q. Now n itself is just the square root of n times the square root of n. And one of them will cancel. So now you put it back together and you get pq over n as a square root. A little bit of algebra. So what we have is that the distribution of sample proportions is going to obey a normal curve, and that the center, the mean of all of the sample distributions is going to be the proportion in the population. Now, if we take one sample and we ask, what is the proportion in that sample? In other words, we take a sample of size 1,000 and we say, what proportion of this sample support Obama? That proportion in the sample is called p hat. Only Yudkowsky calls it p prime. So it's the proportion in the sample. P itself is the proportion in the population. So in the population, you have the true proportion in the population that supports the item, and you have the proportion of the population that doesn't support it. In your sample, you have the percent of your sample that supports it, and you have your percent of your sample that does not support it, and your sample is of size n. So having known that, everything stays the same as it does with means. With a mean, we knew that the error was z alpha over 2 times sigma over the square root of n. Now, why did we choose sigma over the square root of n? Because it was the standard deviation of the sampling mean. Now, for proportion, E is equal to z alpha over 2. But now I no longer have the mean. So what is the standard deviation of the proportion sampling mean? It is equal to square root of PQ over N. This is the standard deviation of the distribution of proportions, samples. Okay. So now, instead of, for a mean, you write sigma over the square root of n, here you write the square root of PQ over n. Unfortunately, if you knew what P and Q for the population were, you wouldn't be doing this. So unfortunately, you don't have P and Q for the population. So what's your best substitution? What's the only P and Q that you do have?
Sample.
From the sample. You do have P and Q from the sample. You wish you had P and Q for the population. That's what you're going to estimate from your sample. So what you do is replace the P and Q for the sample by your best thing, and that is the P and Q. The P and Q for the sample replaces the P and Q in the population. Now, that works for almost all of these problems. So I'm going to do, in Yokowski, I'll do for you 64 through 68. So in Yokowski, could you go to 64 and take a read? Okay, did everyone read it okay? So, Sean, what's it say?
You read the problem?
I'll read it. Use the following information to answer the next 5 exercises. We're working now Yokowski number 64. Suppose a marketing company did a survey. They randomly selected 200 households and then found that 120 of them, the woman made the majority of the purchasing decision. Okay, now, I'm going to ask you this. What proportion of the women in the sample made the decision? Look on the board. A proportion of yeses is the number of yeses over the total number. Now, in this problem, what was the total number of households? How many? 200, right? And of those 200, how many had the women making the decisions?
120.
So what proportion of the households had the women making the decision? 120 over 200. So therefore, what was the complement? What was the number of households that did not have the woman making the decision?
80.
It's 80 over 200. Now, some people like to convert these to decimals right away. So, if you convert that to a decimal, what does it become? 0.6? And then I would expect that this one becomes 0.4. So, we've identified Q prime and P prime. Now, 64, A, X equals what? 120. N equals,
200.
and P prime equals. Now to find the random variable X, so now, what is X in words in this problem?
X is the the sample size,
It's a household.
the household.
It's a household, okay? It's a household where the woman was making the decisions. It was a favorable household, okay? It was a household, or you can just say household if you want, or a household where the women made the decision. Ilkowski likes to nail that down. Now, but P prime is important. So next, what is P prime in words?
P prime is the proportion of the number of yeses over the total household.
It's a proportion of the households in the sample in which the women made the decision. Okay, good. Now, which distribution would you use? Well, we're still only using the Z. We use the Z distribution for all of our proportion problems, okay? So now, it works just the same as it did a moment ago. E, the error bar, is Z alpha over 2, the square root of P prime Q prime over N. So you just make your substitutions, and you construct a 95% interval. So, P prime equals 0.4, 0.6. 0.6. Q prime equals 0.4, N equals 200. And Z alpha over 2 is 1.96, as it always is for the 95%. So the error is going to be 1.96 times the square root of 0.6 times 0.4 over 200. So somebody please find the error. So, Kayla, what you have for that number?
0.06
0.06?
7896.
0.068. Okay, good. Now, that means that we're going to construct our confidence interval. So now what is our point estimate? Our point estimate is P prime, but we're going to have the audacity to say that our point estimate is also the proportion in the population. So the upper limit is going to be P prime plus E, and the lower limit is going to be P prime minus E. So this is going to be equal to 0.6 plus 0.068 and 0.6 minus 0.068. Because we've determined the error to be 0.068. And our best point estimate was 0.6, that was given to us by our sample. So what do these numbers turn out to be? It equals 0.668 as the upper limit and 0.532. So this is our interval. With what percent confidence? 95% confidence. That means that 95% of the time, the population proportion will be in this range, 95% of the time. Good. Now, 68. There's two difficulties that this company might have in obtaining random results if this survey was done by email. So why do you introduce bias if it's done by email? It's because some people don't answer their email very often. And some people don't even have emails. And some people are voluntary surveyors. They love to answer. They answer all surveys that ever come in their direction. And some people refuse to answer any surveys. So you get all kinds of bias if you do it that way. Okay, now I'm going to give you a hard problem. I'm not going to say anything about it. I'm just going to have you guys work it out. Lane number 12. Lane number 12. This is a hard problem. Who's done? You're done. Okay. Can I see your work? Ty, are you done? No. You've done this beautifully, but I don't see part B. Part A is very well done. Now, you don't need to write anything for part B, you just need to think. The second question. You got your answer? Good. Nice work, Heather. Nux, you got some answers.
Yeah.
Okay, what's your answer for A? What's the confidence interval that you got?
2.024
2.024.
and 1.896.
Okay, let's see. Something went wrong. Something went wrong. So hang out on that. Karen, you got some numbers. In all secrecy here. What went wrong here is that P prime is not 16. P prime is X over N. 16 over 25, right?
Oh, okay.
And you probably went the same way. P prime is X over N. X is the number of successes and N is the population. Got it? So P prime is not 16. P prime is 16 over 25. Admirable, very admirable. Very admirable. This is square root sign that comes down here. It goes all the way down, right?
Right.
Okay, we'll make it go down, And check your answers with Kayla there. check your numbers. Does your square root sign go all the way down too, the square root of 25?
Oh, no, that's just how I read it.
Yeah, check your answers with Kayla, I think you got it all. Check your answers, the numbers, I think you got them. But you messed up P. P just wants, no, P, you messed up part P. Check your answers with Kayla. Okay. Tyler, you wanna put your work on the front board here? Part A anyway. So this is lane number 11. And please make your square root signs go all the way down to the bottom, not just close.
That's number 12.
16/25, you gotta put it down, people won't follow you. P prime equals x over n. You gotta just say P prime equals x over n. Because that's what they gotta learn right now. P prime equals x over n equals 16/25. That's where they went south. Now equals a decimal. Okay, and Q prime, 1 minus, yeah. 1 minus P prime, they need to see it, because they're just
P
writing.
minus times minus P. Oh, wait. Which 1 minus, so 1 minus P equals the Q we used to have Q. That's what it's P.
Please write your
minus Q
formula here,
divided by
E
N.
equals Z alpha over 2.
Mhm.
Z alpha over 2.
So,
Subscript.
mhm. And then you multiply. Make it easy.
Close enough, that's just the smart board.
If you multiply them together.
Ah, nice square root sign. The trick is to write the letters first and square root sign last.
And then you.
Oh,
divide
P
that by
prime.
25. And this number, you square root.
P prime. That's a smart board, I'm sorry. Numbers order table. Over n. Now give me a nice big square root sign. I like it. Okay, now you can substitute your numbers. Okay, write your numbers first, square root sign last. Never fails. You can just write that one number now. You assume they can calculate. Okay, so now you can go straight to your interval.
I usually do, so
Ask questions.
Yes,
that's
ma'am.
what I would use.
Oh,
So,
Tayo, Ciara has a question for you.
okay, so if it's 16/25 for P,
Yeah,
wouldn't Q be 9/25?
it sure would.
So I get 0.36, not 0.34.
Oh, that would,
9
Sorry.
divided by 25.
That's a typo.
Oh.
That's a Tayo typo.
Okay. I'm like, wait a minute.
Well done, Karen, stabbed him. Stabbed him right square in the back.
Sorry about that.
Oh, it's
That's
fine.
why I'm sitting over here.
Okay, so that's how you do it. And that's a standard proportion calculation. And there's quite a few of them in Ilkowski and Lane. And they're all done the same way. But now part B is harder. What conclusion can you draw about this test of his ability to predict the future? I'll listen to some input. What conclusion can you draw?
That is proportional.
First, let's get a gut answer. Can this guy predict the future?
No.
No.
Okay, you're wrong.
Kind of.
Well, it's not kind of, this is a statistics class. Okay, now, what does this interval mean? We just took one sample, right? What's the population involved in this problem? What's the population? What's the population?
All coin flips.
All coin flips by this guy for his entire life, right? All coin flips for the entire life of this guy is the population, agreed? Now, we are saying that his proportion for the rest of his life is in this range with a 95% probable confidence level, agreed? Now, if he is perfectly normal, then what is his proportion of coin flips for his entire life going to be? If you're a normal person, what percent of the times are you correctly going to call a head or a tail? 50%, all in favor? 50% is a person that cannot have any special abilities, that's just straight probability, agreed? Does this guy beat the 50%?
Yes.
He beats the 50%, doesn't he?
Okay, I'm sorry, but I have another question.
Just a second, let's let this sink in. He beats the 50%? Because what's his point estimate? Point estimate was 0.64, but his 95% confidence interval goes from 45 all the way up to 82. And if he doesn't have any special abilities, then it should center at 50, agreed? But it centers higher, so conclusion, he has special abilities. Question, Karen?
Oh, no, I see where I made my mistake.
I'm glad I helped you. Okay, good. Okay, now, we know how to do most of the problems in here at this point. And we have to go back to our error estimation for the mean. Z alpha over 2 times sigma over the square root of n. And up until now, we've been sort of sheltered because we've always been told that we knew what was sigma for the population. But the population is what we're trying to estimate, agreed? So we don't know diddly in real life usually about the population at all. So we have to make do with what we have. If we take one sample, what's the only standard deviation that we do have? Standard deviation of the sample, agreed? So the best we can do is replace the standard deviation of the sample into the standard deviation of the population. So E becomes Z alpha over 2 S over the square root of n. This is why Lang makes a big deal between what does sigma stand for and what does S stand for. S stands for standard deviation of the sample. Sigma stands for the standard deviation of the population. So which is the one that uses Greek letters, parameters or statistics? Remember, it's PPSS.
Parameters.
parameters. So which is it that uses Greek letters? Population or samples? Population, parameters, Greek letters. Good. Okay, now, the trouble with making this replacement is that the distribution of sample standard deviations is not normal. It's not a normal distribution. It's almost a normal distribution, but it was worked out by Mr. Gossett and turned out to be slightly different, meaning that you cannot use the z-table. So Gossett gave you a new table that you use instead of z whenever you use the sample standard deviation. E is equal to t of alpha over 2 times the standard deviation of the sample over the square root of n. So you use the t-table, not the s-table. Now those of you that have bothered to print out the t-table that I sent you are now in possession of a t-table. And you read it off a little bit differently than a z-table. First, when you read the z-table, the entry is different for a different sample size. When you read the z-table, because all of the distributions were the same normal curve, the sample size didn't apply. But for small samples, the difference between the t-table and the z-table is greatest. As sample size gets large, the t-table and z-table give the same numbers. But for small sample size, if you are using the sample standard deviation, then you're required to respect that difference and to use the t-table. So when do you use what? Well, also in the printout I gave you, can you find the flow chart that I gave you? Now those of you that aren't doing these tasks are in a hole. So the flow chart that I'm alluding to, it looks like this. So hold it up if you got it. 2, anybody else? Okay, so Tayo, you're in a hole. So Karen, can you lead us through this flow chart? This tells you whether you should use the t-distribution or the normal distribution. So Karen, can you lead us through it?
Right, if the sigma is known.
And what is sigma, please?
The standard deviation
Of?
the mean
Of the population.
of population.
If the standard deviation of the population is known,
And the population is normally distributed.
if the answer is yes,
Yes.
and is normally distributed, then
And if that answer is yes, then you use the z normal distribution.
exactly, you go direct to the z-table if you got 2 yeses.
Right. If it's no, and the sample size is greater than 30, then you cannot use the z-table.
Good. And if you get a no-no, then you just do the best you can.
Right.
You
And
do the
then
best you can.
if it is no, and the population is normally distributed, you have a yes there, then you can use the t-table.
Right.
And if that is greater than yes, greater than 30, you can either use the t-table or not.
And if you get 2 no's, then once again, you do the best you can.
Yeah, you punt.
Got it. Okay, so the t-table is important. Now, the story about Mr. Gossett is that he worked for a brewery. He was a statistician. And he recognized his deficiency in the z-table, that it didn't work well when you had to make this substitution. of the sample standard deviation for the population, especially for small n. So he worked out the table that you should use. And he published it. He called it the t-table. But he was not allowed to use his own name in the publication because of a contractual relationship with the brewery company. So he had to use a pseudonym. So he just said a student. So it's always been known as the student t-table. Later, he was recognized, Mr. Gossett was the student. But it's called the student t-table to this day because of that story. Now, I've suggested that Mr. Gossett be a oral presentation topic, can go into more detail. He did other things as well. And exactly what kind of work did he do for the brewery? That's an intriguing question. What kind of statistics did the brewery need? A good choice. So now let's find the t-table. Now the t-table that Lane gives you leaves a bit to be desired.
In the other textbook.
The other textbook.
Yalowski, or how you pronounce it, they
Lane.
had a link.
Yeah,
and
link.
it-
You found a good t-table.
Yeah.
Good for you. I missed the link. Tayo, did you find the link?
It's in Appendix H. That's all Appendix H is links.
Well, okay. So however you do it, you do get a good t-table. And one way you can do it, by the way, a t-table is not for afternoon tea. It's for something else. However you do it, the easiest way to do it is to read your email and print out the one I sent you, but you can do other things as well. Now, I have a t-table here, and it says the area in one tail or the area in two tails. In other words, are you dealing with alpha or alpha over 2? Alpha or alpha over 2. Good. So the area in two tails would be the total alpha, agreed? And the area in one tail would be half of that alpha over 2. And then you talk about the degrees of freedom. Now, Lane did a very good job in his first few pages of going through what the degrees of freedom are. Now, if you have the entire population, every member of the population is independent, and every member represents a different degree of freedom. So the entire population has capital N degrees of freedom. But if you take a sample, and if the sample mean is known, if you know the mean of the sample, and you try to calculate the deviations, the deviations are x minus mu, agreed? Or x minus x bar for a sample. This is known as your deviation. It's how far all of the x's are from the mean. Now, you can't calculate a deviation until you know x bar, agreed? Now, if I have these numbers, 3, 4, 6, and 7. And these are my members of the sample. Okay? Now, I also know that x bar is equal to 5, which it is. Are these numbers independent once you know x bar equals 5? The answer is, how do you find these? You add up 3 plus 4 plus 6 plus 7, and you divide by 4, and you're going to get a 5, agreed? Now, if you know you're going to get a 5, and I don't tell you what the 7 is, can you figure out what the 7 is? Absolutely. So if you know 3 of the numbers and the mean, then the last number is not independent, it's determined. So if you're making a list of deviations, you have to know the mean to do that, So not all of the deviations are independent, because one is determined by the information we already have. So therefore, the number of degrees of freedom is reduced by one. It's not equal to the size of the sample, but it's the size of the sample minus one. So when you use the student t-table to calculate the degrees of freedom, you take the size of the sample and subtract one. And then you just find the intersection between your alpha value and the degrees of freedom. And this gives you your t-value. This gives you your t-value, agree? So where does the confidence level come in? If you want a 95% confidence, then how does that enter into the t-value that you find? Well, alpha is 5, agree? So you use the alpha equals 5 column, or alpha over 2 equals 2.5. And you get your t-value. And once you get your t-value, then you just put it into the equation that's on the board. So let's go back to Lane. Number 15. Lane number 15. We did A moment ago because you knew the standard deviation of the population, so you could use the z-table. But now, Karen, can you read part B to us in 15B?
Now assume that you do not know the population standard deviation, but the standard deviation of your sample is 10.
Good, so now, when we're given that information, then we no longer can use the z-table, but we have to use the t-table, agreed?
Right.
So 15B, we're going to do this. This is our starting equation for 15B. So can everybody work it out? And you need a t-table. So if you don't have a t-table, you gotta get a t-table right quick, or else get friendly with someone that does have a t-table in the room and use theirs along with them. So Lane, 15B. So E equals T, alpha over 2, S over the square root of N. So S is 10, N is 22, and alpha equals 0.01. Alpha over 2 equals 0.005. And N minus 1 equals 21. So E is equal to. So what's important now is that you're able to read the table and get the correct value for T alpha over 2. I've got my number. See if I got lucky. So Tayo, did you get your T value?
Is it 2.831?
Nice going. 2.831. Karen? 2.831. So now let's do Ilkowski, number 107. Ilkowski, number 107. This problem should take you 15 minutes. Did you do it already? Did you do it already? Okay, 15 minutes, it's a 15-minute problem. Ilkowski, number 107. How kind you are. So we're doing number 107 in Ilkowski, a 15-minute problem. Now, in this problem, you're going to need to use the flow chart that Karen led us through, where you decide which distribution to use and why. So that flow chart's necessary. Well, you have to use something from several weeks ago, and that is, how do you calculate the standard deviation of a sample? How do you calculate the standard deviation of a sample? Actually, this problem would be a good quiz 5 all by itself. Who has found the mean of this sample?
2.25.
True what?
2.25.
2.25. Okay, what's the next thing you have to do? Construct a column of the deviations. So please populate this column, x minus x bar. Populate this column. So Kayla, do you have this column populated? Did anybody confirm that the mean is 2.25?
You got 2.5, yeah.
Yeah, note you're grounded. 2.51. You gotta go slow and not make silly mistakes when you do these large numerical calculations. Speed kills. It's not worth it.
Might as well put 8 numbers in there.
I ran out of fingers. Because I didn't go slow enough. 2.7, 2.8, 3.0, 2.3, 2.2, 2.8, 2.1,
You got 2, 3, 4 pages. Yeah.
2.3.
2.3 is duplicated.
Yeah.
Okay. So if you're working from my list, then it's my bad. But it's your bad for trusting me. Okay, so now we need to populate the column of deviations, x minus x bar. Karen, you have this list? Okay, we need to make this list. For each x, subtract off 2.51 and see what you get. You got that list? Let me put it up there, please. Well, this list is in order, so let me restart. So now the next list, minus 0.41, minus 0.31, minus 0.31, minus 0.21, minus 0.11, 0.19, 0.29, 0.49. Next thing you do is you square the column that you just made. You square them. And you make a new column of those items squared. That's how you do standard deviation of a sample. That's how you did it 3 weeks ago. you get this one column, you sum it up. And you get the sum of x minus x bar quantity squared is equal to some number. And when someone gets this number, please tell me what it is. So 7 of our 15 minutes are gone. So Karen, did you produce that one yet?
No, cause I'm still lost in that second table.
This column?
Yeah.
Okay, well, this first entry, it's 2.1 minus 2.51
Right,
equals minus 0.41. This next one is 2.2 minus 2.51 is minus 0.31. That's where they came from.
right, but then you have two of the 2.3.
Oh, you mean mine? Don't worry about mine, that's just indicative.
Okay,
Don't worry about mine.
okay, cause I was gonna say, I'm
Yeah,
not getting
no, I'm
those
just being
numbers.
indicative up here. Do your own.
Cause shouldn't we be having some negative numbers? Yeah,
Yeah.
okay.
Yeah, well, I got the negative signs. That's a 3? That's a 2, okay. Reading problem. Okay, now they should be going. Now you square each one of those and produce a new column. Okay. So the new column is 0.1681, 0.0961, 0.0441, 0.0441, 0.0121, 0.0361, 0.0841, 0.0841, and the last one is 0.2401. Now you sum this column, and you get 0.8089. Then you go to your formula for standard deviation. S is equal to the sum of x minus x bar quantity squared over n minus 1, and the whole thing to the square root. And this gives you a standard deviation for a sample. So this is equal to 0.8089, and n minus 1 will be 8, and then we take the square root, and we produce it. Now, this is stuff you did 3 weeks ago. So, let's see who gets S first. So this is number 107. So Sean, you have S.
A few seconds.
No.
Point 1011.
0.1011?
That's not right. Oh, yeah.
What, you got, put S.
It's not-
Yeah, you
What's
gotta
this
square
one?
root it, dude, you got one more step.
Oh, crap.
Yeah.
So, like,
318. go back to Ilkowski and answer her questions. A, X bar equals anybody. What's X bar? 2.5, aye? B, S